wrapping up elimination, and then we'll move on to substitution. We want to use elimination to solve this system, so the first thing we're going to do is what? Number these equations. 1, 2, and 3. Okay, the next thing we're going to do is what? Yeah, pick a variable to eliminate. Whichever one looks easiest. We have x, 2x, and negative x there. That might work. We have y and negative 2y there. That one actually could work also. And then we have positive 2z, positive 3z, and positive z there. So for me, if I'm looking at this, I'm probably not going to try to eliminate z just because I have a positive sitting there already, and I need opposites, and that's going to cause me to have to multiply by a negative number. I could use y, I could use z. Which one do you want to do? X? Okay, fine. So now we need to pick two equations to eliminate x. 1 and 3 would be the easiest because we have opposites already. So I'll pick 1 and 3. Again, do exactly how I'm doing this. X plus y plus 2z equals 3. And negative x minus 2y plus z equals 10. We have opposites already, so we're ready to add. Just draw the line and add. X's disappear. We get negative 1y or just negative y plus 3z equals 13. And that is equation 4. That's right. Okay, now we need a different pair of equations. You could go 1 and 2. We've already used 1 and 3, or you can go 2 and 3. For me, I'm looking at opposites and saying I already have opposite signs in 2 and 3, so I'm going to use 2 and 3. So I write down 2 and 3, and then 2x plus y plus 3z equals 7. Negative x minus 2y plus z equals 10. Now normally I would continue to the right here because I'm going to have to multiply my bottom equation by something. I don't have room to do that though, so I'm just going to go below. But normally I would say continue to the right. Draw an arrow over when you do that. Multiplication, just like I showed you how to do with elimination in section 2. We're going to have to multiply the bottom equation by something to make opposites. What will that something be? 2, because we're trying to eliminate x. Once you start eliminating one variable, you have to go all the way through and eliminate that variable again in the second set of numbers. So, like I said, I would rewrite this to the right, but I don't have room. So I'm going to go below the 2x plus y plus 3z equals 7. And then my new equation number 3 will be negative 2x minus 4y plus 2z equals 20. I can draw my line because I have opposites in x and add, and I get negative 3y plus 5z equals 27. Now what? That is number 5. Okay, so we have 4 and 5. What do we do now? Yep. Rewrite 4 and 5 as a system of equations on their own. So here's 4 and 5. 4 is negative y plus 3z equals 13. And then 5 is negative 3y plus 5z equals 27. Now what? Yep, we want opposites again. We are using elimination here. Which variable do you think would be easier to make opposites? It doesn't matter. I'm going to choose y, and that means I'm going to multiply just the top equation by a number. If I chose z, I'd have to multiply the top and bottom equations by something. But I can choose y and just multiply equation 4 by what? Negative 3. That gives me positive 3y up top, negative 3y on the bottom. So now, like I was saying before, I draw my arrow over, and I rewrite my system. It becomes positive 3y minus 9z equals negative 39. My bottom equation stays the same, negative 3y plus 5z equals positive 27. I have opposites, so now I can add. Negative 9 plus 5 is negative 4z equals negative 12. Divide both sides by negative 4, and I get z equals 3. Now that I've done that, what's next? Plug it back into one of the original 4 or 5 equations. These guys right here. Which one looks easier? 4? Okay, so I'm going to write negative y plus 3 times z, which is 3, equals 13, and then solve. Negative y plus 9 equals 13. Subtract 9 from both sides. Negative y equals 4, so therefore y equals negative 4. Now what? Plug both of those into one of the original equations here, whichever one looks easiest. I think number 1 looks pretty easy to me, so I'm looking for x plus negative 4 for y plus 2 times z, which is 3, equals 3, and then solve. X minus 4 plus 6 equals 3. Combine like terms, x plus 2 equals 3. Subtract 2 from both sides, x equals 1. Now you write your ordered triple. 1, comma, negative 4, comma, 3, alphabetical order. Draw your box around it so that I can see your answer clearly. And then what? Check your answer. If that means looking in the back of the book, then do that. If that means checking your answer by hand, it takes 20 seconds. So do it. Up next is using substitution. Substitution is definitely more difficult than elimination. But sometimes substitution actually is way easier than elimination, just depending on the particular type of system of equations you're looking at. A lot of times, like this one right here, you notice that we don't have a z in this equation, and in this one we don't have a y. A lot of times that's a good sign that substitution is actually the better choice than elimination. Basically what goes on in substitution is, just like with a system of 2 equations and 2 variables, you want to pick a variable that's easy to solve for. But then you're going to substitute that equation that you get back into the other 2 equations. Not just the other 1 equation, but the other 2 equations. And that will get one of the variables gone from your new system. Okay? So the same process kind of applies here. We're going to start off by labeling these guys 1, 2, and 3. And now I'm going to create a new equation, equation number 4. But I'm going to do that by picking a variable that's easy to solve for. Which one up here looks like it's probably the easiest one to solve for? The x in which equation? Equation 2. So I'm going to draw a little arrow over here, and I'm going to write down my new equation. It'll be x equals negative 5y plus 9, or 9 minus 5y. Again, you don't need to be in slope-intercept form here with substitution. So I'm going to write 9 minus 5y. I'm going to call that equation 4, just so that I can spot it easily. That's another benefit of labeling these equations. You can see them very easily. Okay, so now what I need to do is I need to take this x. I know what x is now. I need to take that x and substitute it into the other 2 equations. So I'll take equation 3 first, right here. 4z minus 5 times x, which is 9 minus 5y, equals 4. Now I just simplify this down. We have 4z still minus 45 plus 25y equals 4. Yeah, add 45 to both sides. And now you have, and I can rearrange the letters in here if I need to, but I have 4z plus 25 equals positive 49. And I'm going to call that one 5. Sorry, yeah, thanks, 25y. That's my equation 5. Yep, you're going to do the exact same thing to equation number 1. Substitute in x here into equation 1 and rewrite it. So we have 2 times 9 minus 5y plus 3y minus 2z equals negative 1. And then simplify that down. 18 minus 10y plus 3y minus 2z equals negative 1. Combine like terms. 18 minus 7y minus 2z equals negative 1. Get the 18 on the other side. So now you have negative 7y minus 2z equals negative 19. Call that equation 6. Now, as you're doing these problems, if you didn't call this one number 4, then this would be number 4, and this would be number 5. So then number 4 and number 5 would be exactly like the elimination ones. Now we have two new equations, equations 4 and 5. I called this one 4, so now we have two new equations, equations 5 and 6. It's no big deal. It's just I labeled number 4 the way that it is here, so no big deal. I now have equations 5 and 6. Notice that in both of them, x is gone. I just have y and z. So now what I want to do is try to solve one of the equations for another variable. So take a look at the equations and see if there's one that's easy to solve for. So my new system is 4z plus 25y equals 49, and then negative 7y minus 2z equals negative 19. Now when I write that down, notice that I don't have my variables stacked up here. It's not that big a deal because I'm using substitution here. So here's the bummer. In this system of equations, I could solve for this z, but I'm going to wind up with fractions. I could solve for this y, but I'm going to wind up with fractions. I could solve for this y, but I'm going to wind up with fractions. I could solve for this z, but I'm going to wind up with fractions. Okay? What is dangerous is the way that I've written this, it looks like I have opposites right here, but I don't. Why don't I? Because those variables don't match. All right? So be careful how you write these. I always like to make sure that my variables are stacked up. I'm actually going to undo this and switch these two. You don't have to if you don't want to. But this should be a positive 25, thanks, y plus 4z. So now the variables actually line up. For me at this point, I would actually, what, do I have something wrong? Yeah, I just traded these two positions here so that my variables are lined up. And now what I would do, because on a test or something, I'm never going to say specifically solve strictly using substitution or solve strictly using elimination. What I would do here is I would see that I almost have opposites here, and I'd go ahead and multiply this equation by 2 to make those opposites so that I could eliminate the z. Okay? The point of this problem, though, is to use substitution. And I don't want to go any farther than that because of the fractions that we're going to be dealing with. The next problem is a much better example. This one is to get us started. The next problem will actually work all the way through. All right, fine, let's solve it. Using substitution then. So we got to work with fractions. That's okay. So we'll take the bottom equation and solve for z. That gives me negative 2z equals positive 7y minus 19. And now I divide everything by negative 2, so I get z equals negative 7 halves y plus 19 halves. If you need a bucket to throw up into, there's a janitor closet over there. Notice how I'm writing my z's. So now we have what z is. We can take that and substitute it into the other equation. So my other equation is 25y plus 4 times z, which is negative 7 halves y plus 19 halves. Now notice what happens once we do this math. I'm multiplying those fractions by 4, which means my fractions are going to disappear. Okay, so all that throwing up that you just did was for nothing. Now your stomach's empty. So we have 25y. Then 4 times negative 7 halves is the same as 2 times negative 7, which is minus 14. 4 times 19 halves is the same as 2 times 19, which is plus 38, equals 49. 25 minus 14 is 11y plus 38 equals 49. Subtract 38 from both sides, and look, we get 11y equals 11. Divide both sides by 11, you get y equals 1. You ever seen Shawshank Redemption? This is the part where you're slugging through the sewage. And you come out clean on the other side. Yeah, right. This wasn't that bad, okay? I didn't even want to do it, but we did it, and we got through it. So now we go to y is 1. So here's the key to substitution. We have already solved a bunch of equations for a bunch of different variables. We need to find the equation that takes that 1 and lets us substitute in to get the next answer right away. That equation is sitting right here. We can substitute there, and that will give us z. So let's do that. We have z equals negative 7 halves times 1 plus 19 halves. So negative 7 halves times 1 is just negative 7 halves. Z equals, we have negative 7 halves plus 19 halves. 12 halves, which is 6. Now we want to take these two answers and substitute both of them into something that gives me x. And here it is right here. Our equation number 4. Okay. Let me finish. We know what y is, so we can solve for x right here. X equals 9 minus 5 times 1, so x equals 4. So I have my answer. It is 4, 1, 6. Okay, the directions specifically say to use substitution again, so what's the first thing I need to do? Label, 1, 2, 3. What's the next thing I need to do? Find a variable to solve for. Which one are we going to solve for here? Which x? So look, in this one there's lots of choices. You could go for this x, you could go for this y, you could go for this z, you could go for this z. Alright? Just pick one. I heard x first. So in equation number 1, I'm going to solve for x. X equals what? 2y minus z minus 4. Good. What do I do with that? Use it and plug this x into both of these other two equations right here. You don't have to draw those arrows, but that's the idea. Okay? So I'm going to take equation 2, and then I'm going to take equation 3 and substitute that x value in. So equation 2 is negative 4 times x, but x is 2y minus z minus 4. Then plus y minus 2z equals 1. Simplify that down. Negative 8y plus 4z plus 16 plus y minus 2z equals 1. Very carefully combine your like terms. We have a negative 8y plus y, so that would be negative 7y. We have a positive 4z minus 2z, so it would be plus 2z. Then I have this 16 on the wrong side, so I'm going to subtract 16 from both sides right now and get equals negative 15. Now since I didn't label my x equation up here as 4, I'm going to call this one number 4. That's okay. Equation 3, same thing. 2 times x, which is 2y minus z minus 4. And then finish off the equation. Plus 2y minus z equals 10. Simplify. Distribute. 4y minus 2z minus 8 plus 2y minus z equals 10. Combine your like terms, and I'm going to combine y's first because y comes before z, and I want to write y first. 4y plus 2y is 6y. Negative 2z minus z is negative 3z. And then this 8 is on the wrong side, so I'm going to add 8 to both sides, equals 18. And that's my equation 5. Moving on. We have equation 4 and 5 sitting here. So now I'm going to take a look at equations 4 and 5 and see if there's a variable that's going to be easy to solve for. If there is, then that's the one I'm going to pick. If there's not, then I'm going to want to solve for the variable that's going to give me the least nasty fractions. In equation 5, why this one? Right. So if I solve for z, I'm eventually going to be dividing by 3, which means I'm going to have 6 divided by 3, which is a nice number, and 18 divided by 3, which is also a nice number. So if I solve for this z, I will not have fractions. So that's the one I want to solve for. Subtract 6y from both sides. Negative 3z equals negative 6y plus 18. Divide both sides by negative 3. Z equals positive 2y minus 6.
Anytime you say positive, I want to write plus or whatever. Would you like positive 2 from your saying?
Oh, yeah, gotcha. Sorry. So now I know what z is, and I have an equation that has just two variables, z and y. I can take this. If you wanted to label this one number 6, you can. You don't have to, though. But I know what z is, so I can take it and substitute it in right there. We can label this one number 6. Take z and substitute it in to number 4. We have negative 7y plus 2 times z, which is 2y minus 6 equals negative 15. Now we simplify this down and we'll get y. 7y plus 4, negative 7y plus 4y minus 12 equals negative 15. Combine like terms, that's negative 3y minus 12 equals negative 15. I got to get rid of that negative 12, so I add 12 to both sides. Negative 3y equals what? Negative 3. So therefore, y equals 1. So notice the organization here. We started here, we solved for a variable, and then below I write equation 2, equation 3. Then I use that to solve for a variable, and then I bounce back over here and solve for that variable. Now I'm going to bounce back over here and solve for this variable. So I'm taking that answer right there and I'm substituting it into equation 6 to give me z. Z equals 2 times 1 minus 6. So z equals 2 minus 6. Z equals negative 4. Now we plug it into x and we can use this equation right here. All the way back at the very top when we solve for x in the first place. X equals 2 times y, which is 1, minus z, which is negative 4. Be very careful, make sure you're using parentheses as you substitute, and then minus 4. So x equals 2 plus 4 minus 4, which means x equals 2. So my answer is 2, 1, negative 4. And after all that work, check it to make sure you're getting it right. If you start getting absolutely insane fractions, it's probably likely that you made a mistake somewhere. Okay, you can trust that instinct. and you start getting weird numbers. I think I went through the book and specifically picked ones that came up with either integers or maybe like something simple like halves or maybe a fourth or something like that. But if you start getting like 63rds or 125ths, probably a pretty good chance that you got something wrong. You can't escape a section in Algebra 2 without doing story problems, so here we go. You manage a clothing store and budget $6,000 to restock 200 shirts. You can buy t-shirts for 12, polo shirts for 24, rugby shirts for 36. If you want to have twice as many rugby shirts as polo shirts, how many of each type of shirt should you buy? This is assuming that you're going to blow the entire budget restocking. So the budget is $6,000, you're going to spend $6,000. Okay? This is systems of equations. We're not dealing with inequalities. We don't have to make a feasible region, but we do have to define variables and we do have to come up with a system. So, start with variables. What are the variables here? So, we have t-shirts, and we have polo shirts, and we have rugby shirts. And I'm guessing you want to use what for t-shirts? T and P and makes sense. As you write these systems, you can put them in alphabetical order if you want to. Doesn't really matter. We're just going to go through the information that we have. A budget of $6,000 is probably important. Restock 200 total shirts, probably important. And then also we have prices for each shirt, probably important. Those are three different things. Price, budget, number of shirts. We also have one other piece of information here that's important. You want to have twice as many rugby shirts as polo shirts. So however many rugby shirts I have, I could divide that by 2 and get polo shirts. Or I could say how many polo shirts I have and then multiply that by 2 and get the rugby shirts. Okay? So let's come up with some equations here. In fact, let's come up with the equation for that situation. Twice as many rugby shirts as polo shirts. I want twice as many rugby as polo. So if I have 10 polo, how many rugby do I have? So make sure that it matches up with that logic, okay? The question is, where does the 2 go? I have polo and I have rugby. If I double the amount of rugby shirts, do I get the number of polo shirts? I have twice as many rugby shirts as I have polo shirts. So I have to double the polo shirts to tell me how many rugby shirts I have. Okay, that takes care of that. Now we have a budget of $6,000. So I'm going to spend $6,000. We're talking about dollars, so I probably should come up with some dollar stuff on the other side. So I'm going to use the dollars information. T-shirts cost 12, polo 24, rugby 36. What do I write? 12T. Yeah? Equals $6,000. That's all dollars. So that's your second equation. Now come up with the third. There's your system of equations right there. Now the question is, which is going to be easier to use here, substitution or elimination? Why substitution? You're right, but why? Yeah, you already know what R is. So I can take what R is and substitute it into both of these equations right here and then suddenly have a new system of equations with only 2 variables. This does not say specifically solve using substitution or elimination. We can use one or the other or both at any time if we want to. But substitution right now works great. So I'm going to take this equation right here and plug it in right there for R and right there for R. And then rewrite it. So I'm drawing an arrow over, and I'm going to have 12T plus 24P plus 36 times R, which is 2P, equals 6,000. My second equation will be T plus P plus R, which is 2P, equals 200. Then I combine like terms. I get a new system of equations. 12T plus Well, 24p plus 36 times 2p. 36 times 2 is 72. 72 plus 24 is 96p. Equals 6,000. And then this one becomes t plus 3p equals 200. So from here, you could use substitution or elimination. Which one looks easier? Elimination. We could multiply this bottom equation by negative 12 and use elimination to get p by itself. Make sense? Okay, so let's do that. Multiply the bottom equation by negative 12. When I do that, I don't have any room, so I'm going to write below. I get same top equation, 12t plus 96p equals 6,000. Bottom equation, negative 12t minus 36p equals negative 2,400. Have opposites, so I can add 36p plus negative 96p plus negative 36p, something 0p. 60 equals 6,000 minus 2,400, something 00. 36. So 60p equals 3,600. Divide both sides by 60 and I get p equals 60. So I'm buying 60 polo shirts. Now I'm going to take this information and plug it back into something to give me another variable. Which equation am I substituting into? This one, 2p equals r. Because 2p equals r and p is 60, then r must be what? 120. And now that I know that p and r are 60 and 120, I can substitute that into this equation right here. P plus r, t plus p is 60, plus r is 120, equals 200. So t plus 180, that's a plus, equals 200. So t equals 20. And now that we've done that, we can write our answer. This is not an ordered triple. This is a story problem, so we have to actually answer the problem. Buy 20 t-shirts, 60 polo, and 120 rugby. There's your answer. So the bottom part is kind of a follow-up to the original problem. Suppose you want to have the same number of t-shirts as polo shirts. Buying 200 shirts with a budget of $5,400 now, how many of each shirt would you buy? So I want to have the same number of t-shirts as polo shirts now, okay? That doesn't mean I'm using this answer. It means in my original problem, how does that change stuff? Also, I don't have $6,000 anymore. I have $5,400. So that changes stuff as well. What would my new system look like? Yeah? I want the same number of polo as t-shirts. Yeah, P equals T. Then I want 200 shirts, and I want a budget of $5,400. So let's take care of 200 shirts. How do I write that? T plus P plus R equals 200. Same equation as before. And then finally, same prices. 12T plus 24P plus 36R. But now instead of 6,000, it's 5,400. So let's talk about how we would solve this system in red. What would we do? Substitution. Where? Right, so whichever one you want. You could take P and substitute in for T. So that would become a P, that would become a P. And then you combine like terms and then do what we did over here. Elimination or substitution to solve. Or you could take T and plug it in for P. So you'd have a T here and a T here. Either way, you combine like terms and then you have a new system of equations with two variables. So we're sitting over here again, but instead of these numbers, they're a little bit different numbers. Use elimination and solve. Okay? So just because the numbers change a little bit doesn't mean like the entire problem is completely foreign to us. We just have a new system of equations here that we can work with the same way that we work with this one. So the idea is recognize when to use substitution, when substitution is appropriate, when elimination is appropriate. Substitution is definitely appropriate on this problem because of this case right here and this case right here.